Hey, can everyone hear me? Awesome, sweet. Yeah, so I'm going to talk a little bit about the latest network upgrade to the Avalanche network, which is Cortina. The main thing in Cortina was the X-chain linearization, and so in order to talk about that, I'm going to have to talk about Avalanche consensus as a whole, which up to this point, I've avoided giving presentations on Avalanche consensus because it's really complicated and I found it really hard to distill. So I'm going to rely really heavily on images, and I'm going to rely on you guys to proactively raise your hands and ask any questions at any point in time when things start to not make any sense. So hopefully together we can make this a good presentation. So yeah, anyways, so this presentation is concretely how to linearize a DAG in approximately 72 moderately difficult steps. Let's kick it off. So first off, a little bit of an explanation on who I am. I've been working at Ava Labs since before Ava Labs existed. So I started working with Goon in 2018, and the company ended up forming in early 2019. And I've basically been focusing on all things platform. So what that realistically means is focusing a lot on AvalancheGo, and yeah, so pretty much anything platform has been my kind of forte for the past 5 years almost. Outside of specifically just Avalanche stuff, I'm in general really interested in algorithms and data structures. So I've been known to talk at length about that pretty much until people tell me to shut up and go away. So if you want to learn about that, or at least talk to me about that, maybe I can learn something from you guys too. Yeah, I'd be super excited to chat. And then also, I'm a really big skier. So if you guys have ever ran AvalancheGo, you'll see a little like skier at the top, and that's my little my primary addition to the Avalanche kind of like validator UX. And so I've kind of hidden that throughout the whole slides of the presentation. So hopefully you guys can see it. Some of them are really well hidden. So yeah, anyways. So kind of already talked a little bit about this, but more concretely, we're going to talk for a lot of background for the Avalanche Avalanche consensus, and then talk a little bit about Cortina at the end, because pretty much this whole thing is background on Avalanche consensus. So we're going to start off with Snowball consensus, quickly go over what a DAG is, talk about Snowstorm consensus, which I think a lot of you might have never heard about, but it's kind of the backing of Avalanche consensus. Then we'll finally get to Avalanche consensus, and finally the very last part of this is Cortina. So we'll see how it goes. So quick background on consensus. All consensus is getting the network to agree on a value. So if you have a bunch of people in the network, some people are proposing a 0, some people are proposing a 1. You don't necessarily know which one is right. You want the whole network to agree on that value. So some people think that in like Avalanche subsampling, you're trying to vote like yes or no on a transaction. It's not really yes or no on a specific like including something. You're just trying to decide yes on something, right? So if there's only one option, it's an easy choice. If there's multiple options, that's when consensus has to come involved. So there's really no correct answer. You just kind of have to pick one and move on. So this little example here is the red pill, blue pill. You got to pick one. Whichever one you pick is fine, right? Maybe. So how does Snowball actually perform consensus? So if you guys have seen my previous talks, you'll probably be wondering, okay, I've seen this a lot. I've seen this so many times. Goon has said this to death, so I'll try to cover it really quickly, but hopefully we'll get to some new content. But initially, nodes just kind of pick our color arbitrarily. So in this case, we're trying to decide either red or blue. These little circles are supposed to represent nodes in the network. So you might have like, I'm running a laptop, I'm running a red node right now, someone else in the network is running a blue node. We need to all agree on a color. Initially, people just pick them arbitrarily. Avalanche, or Snowball in this specific instance, will essentially randomly sample peers in the network. So in this case, the red node that is circled is sampling 2 blue nodes and a red node. Because it sees a majority blue, it's going to adopt its color to be blue. And if you just keep doing this, because of general instability in this process, you're going to end up cascading or avalanching, as some people like to say, to one side. So if you keep doing this over and over again, random perturbations will guarantee you're eventually going to go to one side. In this case, everyone went to blue. So that's the basic idea of how Snowball works. I don't really want to go into too much more detail specifically on Snowball. This is kind of the overarching mechanism that is used in the background for all of the consensus work. Now, I want to cover briefly some background on just what a DAG is. So at the end of the day, a DAG is just a data structure. There are vertices. So in this case, we have 5 different vertices in this graph. The graph has edges. So edges connect vertices together in some way. Because it's a directed graph, they have a direction. So you can see here that there's arrows pointing from vertex to vertex. But in this case, there's actually a cycle. In an acyclic graph, you can't have a cycle. So a good example of this is like a hash graph. So you have like pre-images. You're guaranteed that you can never like reference yourself. And these types of graphs are useful for a various number of algorithm problems. So a fun example, if you've ever written a compiler, congrats. But inside of compilers, you end up needing to do register allocation. And register allocation is essentially analogous to some level of coloring of these graphs. And this is actually a really difficult problem, so it might not be a great example, but this is one way that graphs are used in like more traditional ways of representing data. So now I want to basically use these 2 mechanisms together. So Snowstorm is all about representing Snowball as a graph. So in this case, we have two transactions. We have a left transaction and a right transaction. The left transaction is green, the right transaction is red. The reason that they're green and red is because green I'm going to represent throughout the rest of this kind of slide here as being accepted and red being rejected. You'll notice that the edge is directed in this case. So in a Snowball representation of a DAG, or of the Snowstorm representation of Snowball, the edge represents preference. So because the left transaction is accepted, it's preferred over the rejected one, right? The reason that it has an edge at all is because these transactions conflict. So inside of, like, say, the Avalanche X chain, these would be perhaps 2 transactions that consumed the same UTXO. So there's a conflict in this conflict set between each other. The reason why I'm trying to represent this as a graph here is because you can now represent multiple different ongoing transaction decisions. So previously in Snowball, you had just these red nodes and these blue nodes, right? But in an actual network, you're trying to confirm multiple transactions as you go, right? So in this case, we actually had 4 transactions issued. Each had a conflict. And so one transaction, the top left transaction ends up being accepted. Bottom right transaction ends up being accepted. Yeah. You'll notice that a key invariant of this kind of coloring mechanism is that every green transaction, every accepted transaction, it does not have an edge with any other accepted transactions. That would represent a double spend. So if you have 2 green vertices touching each other, then that's a safety failure, and the whole platform team is definitely getting paged. So no bueno. Also, in order to reject a transaction, so have a red coloring, you have to have been rejected by an acceptance. So this is a really nice property for traditionally issuing virtuous transactions. So throughout most of this talk, we'll probably be talking about kind of the unhappy path. But in these kind of examples, we have a little bit more of a complex representation, and you can see there's a green node here that has no edges. That's the traditional path, where there's essentially no conflicts. People just issue their virtuous transaction, and it gets accepted immediately. You can also, though, have much more complex kind of subgraphs. These conflicts are not necessarily transitive, so you can see there's some transactions that A conflicts with B, B conflicts with C, but C does not conflict with A. As an example, you can see on like probably the top or the bottom left here. Yeah. So how does polling work in this situation? So I used to be polling saying, hey, what is your color, red or blue? And I'm going to take the majority. Well, now what ends up happening is I poll you and I say, tell me what all of your preferences are. Right? So you initially specify the preferences the same, but now rather than just responding with a single color, red or blue, I'm returning the entire set of preferred transactions. So in this case, a transaction is preferred if it only has inbound edges, right? So you can see that there are some cases where transactions, so say like this like leftmost red node here has 2 inbound edges, but there is 1 outbound edge. Because of that 1 outbound edge, it is not preferred, even though it is more preferred than some other transactions. So you can see through this sampling process, we might initially accept the virtuous transaction. We might start to prefer some other transactions. We go through accept, reject some, and we keep moving on. The core problem with this is that this is pretty much a very theoretical consensus mechanism, because if I have to, every single time I'm polled, give you the entire set of transactions that I have ever accepted, the bandwidth usage is going to be linear in the total size of the blockchain per poll, which is not great. Not great at all. Anyways, so the problem here is exactly that. How do we reduce the bandwidth and end up introducing optimizing the polling process? So the idea here is, well, we introduced the problem by adding a DAG, so we should add another DAG. So in this case, I end up representing vertices, which are the more traditional Avalanche vertexes that are accepted on like the traditional like networking protocol. So vertices are the things that are actually containing the transactions. They're like much more similar to blocks. And vertices contain transactions. And in this case, you can see I have these dashed arrows that represent that a vertex contains a transaction. So, and then the large arrows for the vertices are representing parent dependencies. If a vertex only contains preferred transactions and its ancestry only contains preferred vertices, then the vertex is said to be preferred. Similarly, if it is accepted, if all of the transitively referenced transactions are accepted. So we can see here, if we go through the voting process, we end up maybe accepting the top virtuous transaction, which accepts the vertex. We go through again, we might end up accepting another transaction, which rejects another transaction. Once any transaction is rejected in the transitive ancestry of a vertex, that vertex ends up being rejected. So you will never report that as preferred. And you can keep going through here until you eventually get to a situation that in the right here, everything is accepted or rejected. So this is kind of a stable state equilibrium. Nothing is going to be happening until we introduce a new transaction. Now, a couple key insights here is you can, in this case, if someone asks you what your preference is, you can just respond with the bottom green vertex, because that implies that you prefer all of the transactions in that ancestry. So now when I query you and I say, hey, what transactions do you prefer? You don't have to respond with the full set of all of the transactions you ever have accepted. You just have to respond with essentially a cut of the DAG that references all of the transactions that you prefer. Additionally, once you reject something, you'll never prefer it, and you're only telling people things that you prefer. So you can actually just delete all of the rejected state. If you had to keep the rejected state around, that would be a major DOS vulnerability, because people can just issue a bunch of transactions that keep getting rejected. So what's kind of the catch here? The main interesting part about the DAG is that it does not provide any total ordering, right? So you can see in this case, we have a totally valid DAG with only virtuous transactions, which is a very normal case for Avalanche. And we have two different possible representations that a node might see during this execution, where we could have one transaction accepted in a different order than the other. What that means is these nodes might not actually end up seeing the same exact state at any given time. And it turns out that for a number of reasons, this is kind of important. So a lot of state sync primitives, which essentially allow you to join the network, require to have some form of a fix point or a linearization point to be able to join in and have everyone in the network understand that that was a point in time and state that they can sync to. Also, there's a lot of issues with load balancing of APIs or like exchanges that want to be able to index stuff in a canonical order. Basically, a lot of people have spent a lot of time integrating with blockchains and not so much with DAGs. So there's a couple technical challenges, and then there's a lot of integration challenges as well. So the goal here was, okay, how can we make it so that all of the nodes end up agreeing on a global state at some point? Not necessarily at every point, but at some point we want to be able to guarantee that invariant. So the idea was, okay, we can add a new vertex that says, once this is issued, it conflicts with anything that either it does not transitively reference or that does not transitively reference it. So in this case, we have this red vertex that does not reference the kind of, it was gold. I think it's now a little bit more pink on this, but anyways, pink stop vertex. And so they conflict. But if we remember the previous kind of assumption on when you would accept and when you would reject a vertex, you can see that this red vertex actually only references accepted vertices, and it contains only accepted transactions, right? So previously we would say, okay, our vertex should be able to be accepted at this point. So our vertex acceptance rule is now no longer sufficient. We have to somehow introduce new conflicts to these vertices. So as we do, the rabbit hole goes a little deeper. Now we have these special transactions that aren't actually transactions, but they're registered as transactions inside of the Snowstorm conflict graph. These are represented as these kind of diamonds on the right side. So the right side is like a Snowstorm part of the graph, and the left side is the Avalanche part of the graph. So you can see here that for almost all of the vertices, there are no actual conflicts on the what we call like vertex transactions, except for the one that does not meet the rules of being transitively referenced or transitively referencing the stop vertex or the linearization vertex. So those special vertex transactions actually do have a conflict. So essentially what we ended up doing was introducing new transactions into every vertex so that we could still use Snowstorm's polling and agreement mechanism to then ensure that at the Avalanche DAG level, we get that globalization linearization point. You get a nice property here where you could end up rejecting the stop vertex, but once it is accepted, and if it does get rejected, you can essentially just reissue another one. There's no real major overhead. Once you get it accepted, it will guarantee that everything up to that point has gotten basically a canonical state in a global view. Yeah. So now I want to talk a little bit just kind of on where the X chain is now. So on both Fuji and mainnet, we've already activated the linearization. So that means that this process worked. Nice. And essentially the X chain was able to accept its linearization vertex, which gave the network a part of a global accepted state, such that we could actually safely transition into Snowman consensus. We could have technically used this linearization point to then re-kick off a new round of Avalanche consensus, but that really only solves the technical challenge of state sync and not all of the other various integration challenges of actually using the DAG. And so we felt that it made the most sense to essentially align everything with Snowman and Snowman++ for both warp reasons, state sync reasons, and integration reasons. So is the DAG gone forever? Probably, but I'll never say never. But yeah. A couple points that I want to clarify, because I have seen this as a point of confusion, is that people really felt that the DAG is what gave Avalanche its scalability properties, its fast finality, high throughput. And really, the Snow subsampling is what gives you this capability. So Snowman is really just a special case of Avalanche where you're guaranteed to have a linear history. You're still doing the subsampling process that makes Avalanche consensus be able to confirm transactions in blocks rapidly with low overhead. Technically, with the DAG, you get to avoid having a mempool because you can essentially just issue the vertices on any node and it'll get added in a nice generic way. But realistically, mempool latency times are probably on the order of like a second if you're doing it right. And it actually could decrease, the DAG could actually decrease your theoretical throughput because you aren't able to actually batch and parallelize the transaction execution as easily as in a block, which might be confusing because you think a block is totally ordered, whereas a vertex is partially ordered, so that should result in being able to be more parallelized. But it's actually more of a question of how the underlying data is structured. So the X chain is still UTXO based. It's still naturally parallelizable inside of the actual block. And so that block execution can actually be performed faster. And yeah, and now we get to work on state sync and other fun and interesting parts to the X chain. So at this point, I think I have around 5 minutes left. I know I said that I was relying on you guys to ask questions. You have totally failed up to this point. So I know it wasn't that clear. So if you guys have any questions, mayonnaise might be an instrument. I don't know, but we can figure it out. So yeah, are there any questions here? Yeah. Sorry. Yeah, there'll be a mic that comes over. Yeah.
Hello, Stephen. Does this change somehow influence the block producers, the set of block producers or their orders because with the DAG, I had the impression that anybody could, add transactions to the DAG, but with the linearization, you somehow have now this constraint.
Yes. So with all of our Snowman-based chains, we use Snowman++ to represent proposer lists as kind of the initial set of people that could propose a block. In practice, the X chain has really low throughput and usage because generally people are much more interested in like the C chain, like dApps, or like staking on the P chain. So I would actually be pretty surprised if the X chain was using the proposer lists a lot. The proposer VM or Snowman++ really only activates if you have consistent load. So the answer is technically yes, but in practice, I don't think that the X chain actually has designated proposers. Yeah. Good question, though. Very good question. Any other questions? Cool. I must have nailed it. All right. Thanks, everybody.